try and see what we get.
Hello? Okay. Yeah, I can hear myself. That's all I really need, isn't it? So, yeah, if you've been looking for good corn, you came to the right place. Actually, I think probably this is my best plot site in North Carolina, so that probably tells you a little bit about how good this is across the state in comparison. And quite frankly, after hearing my colleagues in the Midwest talk, I wouldn't be surprised this is some of the best corn in the United States this year. So indeed, if you want to see some good corn, you've come to the right place to do that. We've got a couple of tests here that you might want to take a look at. One is the one over there behind the trailers, or behind me facing it anyway, behind you. That's our typical high management test where we have a conventional system. Basically we do starter and some of those things like you do, or most of you have done in the past. And then we add treatments to it. This year our treatments include a micronutrient treatment at V4. So we put some micronutrients on. I've been talking about how we need more magnesium and boron in these plants, particularly if we're going to get good flowering. So we did that at V4. We've got some placement, a Y drop. In fact, we got the Y drop that we used right over there, so you can take a look at that. So we got Y drop placement, and then we got some nitrogen at VT, plus we've added, again, a higher population. So there's 38,000 plants at seeding versus 34,000 at seed. So you can see the impact of population in this environment this year. So there's some, oh, I can hear myself not even as well here. Anyway, yeah, so you can see what the impact of some of those treatments are. I got a chart over there. So that's about all I'm going to say about that. But you're welcome to take a look at it. Plenty of time to do that. I'm going to spend most of my time talking about this test behind me. This test here comes as a result of questions that I get. We get lots of flyers, newspapers, magazines, advertisements about different products, companies promoting products that we hadn't heard about, or talk about issues that we didn't really think about. So we're going to, some of those products are in these, there's 12 different products in this trial here. So we're going to reveal those, like those home makeover deals where they send the homeowner away and then they reveal it to him later on. You're going to be about as surprised as they are. So at any rate, anyhow, so that's what this test was about. But I want to spend a little time before we look at some of these talking about what you really need to be thinking about as you think about whether I need to add some of these products to my management plan. Not only do they make more yield, but what are they doing for me in the scheme of my soil and plant environment? We're really good at managing what we can see. We're really good at looking at plants and saying, yeah, they need to be greener. I can manage that. I can manage what we can see. We're not so good at managing what we can't see. And that's the problem with our soils. There's lots and lots going on behind the scenes that we can't see. I fell in the hole. My wife has said I've been in a hole all this time. Anyway, they talk about a teaspoon of soil having billions of millions and billions of microbes. Lots of activity going on here. So the biology above ground is mimicked and probably even enhanced by the biology that's going on below ground. So I want to talk about, that's what some of these products should be doing, is enhancing our below ground biology such that we're seeing a result in our above ground. Furthermore, that's how we sustain ourselves. It's our soils. Every farmer knows, a good farm has good soils, and that's exactly what you're at. It's enhancing your soils, enhancing the biology of these soils. So let's talk a little bit about that. Then we're going to look at some of these products, whether or not you see any evidence that they're enhancing the biology of our soils. And then we're going to talk a little bit about the other issue that came in this year, which is temperature. There's basically 6 different organisms that inhabit the biology of our soils. And they're on this chart from the smallest to the largest. There's single-cell bacteria, or even multiple-cell bacteria, that work in our soils all the time. They're at work right now today, transforming nitrogen. And we'll talk a little bit more about what they do, but lots and lots of my biology is the bacterial biology of these soils. Fungi. Fungi, mycorrhiza, we've heard that term. It works with the root to help promote the transfer of nutrients and water to the root hairs. So fungi benefit us in multiple ways. They can actually attack insects or nematodes. We've seen products on the market that are biological products that attack nematodes. That's what some of those are made of, is fungi or bacteria. Protozoa, single cell, you've heard Pythium. Is oziumite. It's sort of a protozoa type organism that works, they're mostly often found in water. So the water component of the soil contains protozoa. Nematodes, of course, we've heard that before. We don't think very highly of nematodes, but actually they're beneficial nematodes that are in our soils that benefit our crop production. Anthropods, those are those, everything that crawls and creeps in our soils there. Stuff that my wife goes, ooh, I don't like that multi-leg thing there. That's an anthropod. And then, of course, there's earthworms. And that's most of the time when we talk about health of soil, we talk about more earthworms in that soil. Well, that's part of that biology, but just a minor part compared to this bacteria and fungi, which really are the drivers for the health of our soil, as well in those small organisms that are working down there. So I just briefly want to say, when do those work? Where do those work? Where are they most predominant that we have the biology, particularly bacteria and fungi, working? Well, first of all, this is seasonal, so this is the middle of the summer here, early, late summer. You can see they work when it's warm and moist. They're just like anything else. They work by temperature. They like it when it's warm and moist. When it's cold or when it's wet, their activity is much reduced. So indeed, they work basically better when it's warm and moist. And then where are they? Well, most of them, the reason that line goes way out there as it gets closer to the surface of that chart there, is that most of them are in the very surface of their soil. They need oxygen. That's been our problem in the Blacklands, is having oxygen in our soils. When we get more oxygen, we get more bacteria and fungi in those soils. So they're close to the surface, mostly working in that warm summer environment. Now, I'm just going to speak a little bit to bacteria, but keep in mind that fungi are just as important. Lots of different bacteria in our soils. We got nitrogen-fixing bacteria. You guys know that's how we get away with applying urea. Bacteria work on it, transform it into ammonia, and eventually into nitrate. So we get nitrified bacteria. We can convert nitrate back to gas if we put them under anaerobic conditions. The anaerobic bacteria work off of the oxygen and nitrate to survive, and therefore they produce NO2 gas. And then we got acetomites. They decompose the large residue that we see here on the surface. Bacteria are working on those. So there's the acetomites. The fluorescens are antifungal bacteria. And then we got the cyanobacteria. These are actually rarely found in many soils, but they are found in our soils to some extent. They actually work with nitrogen in the atmosphere and fix nitrogen in our soil. So you can see the wide range of activity that's going on down here. Lots of things happen in here below ground that we can't see here. Now, what do? Well, they decompose. They're mutualists. They work with the plant in providing nutrients, whether it's nitrogen, sulfur, other vital elements have to go through a bacterial conversion process. They're helpful in the form of attacking things that attack our corn, or they can attack corn. We can get biological blight on our corn and attack galls on the roots. And then they're chemotrophs. They obtain energy. I just mentioned the anaerobic bacteria that causes nitrate to be gassed off there through a denitrified. That's a chemotroph. They're gaining energy from that molecule. So that's a range of things that these bacteria can do in our soils there. So indeed, first thing you want to think about as you think about what can I do to enhance my future is how do I enhance the good bacteria that are working in my soil? How do I work with them? When do I need to work with them? Under what conditions do I need to enhance them? So if you can answer some of those questions, you can start answering whether I need some of these products that are out through here in your farming operation. Now, we've talked about the biology. There's one other aspect to this health, this soil health issue, and that is energy. You know, they say if you want to know a man's priority, go find out what he spends his money on. That's true. Or if you want to know a man's priority, go find out where he's eating at, you know, because that's true. We're driven by those things. That's the same with your biological activity under the ground. They're driven by their need for energy and where their food source is, and their most important food source is carbon. That's why we often associate soil health with carbon, because carbon is the energy source for this below-ground biological activity. It also, as Charlie mentioned, acts to hold chemicals or nutrients in our soil. Lots of functions that carbon has. Carbon is essential in this process. We could add all the microbes in a jug that we want to into a soil without carbon, and we will get nothing without the energy to help them flourish and perform their activity. So the two have to go hand in hand, is to have the microbial population and the energy. So what kind of carbon do we have? Well, there's lots of forms of carbon. You're well aware of this. We got carbon in this residue. That's a big organic chain, most of the time piled up in fibers that are difficult or slow to decompose. We got some carbon that's a little bit more decomposed, but still in long fibrous chains, long chain carbon. Those are essential. They help in soil structure, but they're not what the microbial biomass needs for energy. What the microbial biomass needs is short chain carbons. And those carbons are well known as fulvic or humic acids. Here's a if you're into chemistry, you'll love this. There's a chemical formulation for a humic acid here. These are essential. These short chain carbons are essential. They provide the ready-made food for these microbes. They also provide energy. These short chain carbons have a lot of electrical charge to them, so they actually drive forward reactions in our soil, almost acting like a microbe themselves. The molecule actually acts sort of like a living thing. So indeed, these are essential. The problem with these short chain carbons is they're the most readily burned off, oxidized. So if we get weather or hot, dry weather, they oxidize, or if we're stirring that soil through tillage, they're the first things to go. So believe it or not, even on a soil that looks as nice and dark as this, oftentimes we have a shortage of these humic or fulvic acids in comparison to the larger chain acid or carbons that we have here. So it's essential that we keep in mind that what kind of energy these microbes need. It's these short chain carbon molecules that are important to them. So we have to have both of these things working in tandem if we're going to be successful in promoting that soil community and that soil health underneath the soil. Now, you know, we're going to look at these products here in a second here, many of which promote either the providing of that short chain carbon. In other words, you see humic or fulvics now used more commonly in agriculture, not just here, but across the United States. There's others that actually work from adding a biological product to the soil, whether it's the extrudate from bacteria or fungi that actually do the work in the plant, or whether it's the fungi or bacteria themselves in a stasis form that can actually then start to multiply under moisture and better conditions. So these products provide a different approach. Each company has a different approach to adding these products to enhance that microbial. They do have some effect. The reason I put these charts in here, we've done some work over the last 2 or 3, 4 or 5 years actually, and you can see not a huge yield increase there, about 12 bushels there with a product here that was significant difference in yield. The real issue there was how much did my cost, and actually in this case this product was cheap enough that my cost was low enough that they actually added value to my bottom line. So you can see a result we got there. Here's another biological product that's more well known actually in this area since it's associated with nutrient, but it's a biological coating for fertilizer, and you can see here between the check and several different treatments using that coating with or without fertilizers added, why we had some significant increases there. And again, in fact, there was pretty good 17 bushel, almost 16, 17 bushel difference there. So you can see we've gotten some positive results. The issue is knowing what you need. Do I have the carbon resource that I need to stimulate the biological activity? Maybe I just need this biological enhancement. Maybe you don't need any of it. But it's knowing what you need, what's going on. And guys, this is the future. This is where it's going. We're going to see lots more of these products coming on the market. We're going to see a lot more claims. We've got to decipher these things by knowing what they're going to do to enhance our community on our soils. And that takes more than just looking at yield and some of these other things. It takes looking at how they change the short-chain carbon in our soil, how they're enhancing the number of bacteria, those kind of things. Those are the kind of work that really, and that's the nice thing about having new people in crop science. We got people who are going to be looking at that. We got Plant Science Initiative. That we're in position to know more about these products. So today we're going to look at them in this situation here. Now, yeah, the best differentiator here is yield. And I don't have yield for you. But we're going to look at this. Now, there's other things you can look at here as we go down these plots and reveal what's there. Things you like to look at is plant height. Now, this is all the same hybrid here. All at 34,000 seeding rate, probably about 32,000 plants to the acre sitting in here. They're 60-foot rows if you want to wander back in there. Lots of row to look at. So plant height gives you an idea because stress early on affects plant height. So if it relieves stress by enhancing the interaction between the root and the soil, in some cases some of these products work directly on phosphorus availability. They bacterially work with phosphorus in the soil to help release phosphorus. So indeed, that's a factor. Phosphorus certainly is a factor in increasing plant height. So indeed, plant height is something we can look at here. The other thing that I've got here, if you're interested in playing with it, is a calipers. I can actually measure the width stalk diameter of these stalks, and that tells me a lot about how long and how well those stalks put on cells all the way through tasseling. So stalk diameter is a very useful tool in looking at early growth and measuring impact on growth there. We can look at, of course, ear size here, and I'm going to show you examples. You know, this is one of those years. Normally, the best corn on a plot tour is the ones that I reveal at the end of the plot because they had all the sunlight and moisture they needed. So it looks really nice on the outside, but you get back in and you don't see very good ears after a while. Well, that's not true here. That's not true. These ears inside are looking just every bit as good as these ears on the outside. So this is good corn here when you can see that. So we can look at these ear size here. The other thing we can look at is root. You know, how much root material do we have, biomass, how long or how thick are some of these roots, how deep do they go? I've excavated a couple of examples, that's the hole I about fell in, to show you what some of these look like in situ. So that's another way to judge whether or not, how prolific these roots are developed, because it's all about roots. That's what these bacteria are interacting with is these root systems. They should improve roots. Now, some of these materials also interact with soils and build in soil structure. So, and again, it's all about fungi and bacteria working together to build those granules in our soil. So those are things that you can look at as we go down and look at these treatments. So with that, I'm going to move down to the end. You're welcome to join me. And we're going to look at each of these plots and reveal what's there. And then you can make your own judgment as to what is valuable or not, or you may just say that you're going to reserve judgment until the final yield and cost come in. And I'm going to talk a little bit about where these products fit into our into what we're trying to do here. So there's like I said, there's 12 products down through here. So I'm going to reveal this first one. And this one is called Monty's Midnight. Now, Monty's has made their name on humic acid. That's what the company has as a base, is developing products based off of humic acid. So you've heard the term liquid carbon. There is actually a Monty's liquid carbon plot here. So we'll see how this compares to that plot, Monty's liquid carbon alone. This product has the liquid carbon plus a micronutrient. So they bound it with some micronutrients. The liquid carbon is supposed to help stimulate that biological activity and help uptake those nutrients. That's what it's all about. So this was applied at B3 at 2 quarts to the acre. Here's the plant that comes from it. That's again, you may say, well, that can't be a typical. No, go out there and look if you want to. And here's the root system under that plant there. Not as deep maybe as I would have liked to, but still pretty nice development. Now, you notice these roots, by the way, these plants were almost knocked flat by a storm in early June. I mean, they were on the ground. So what's happened here is those plants, they responded to light, and when they respond to light, they start putting out roots on the dark side of the plant to try to anchor that plant better as they curve toward the light there. So that's a growth regulator effect you're seeing. So it sort of skews how we look at roots here under this plot, but that's what's happened here. All right, so there's the addition of the energy source. That's what you want to think when you think about that plot. Did that addition of an energy source help there? Here's the next one. Now this actually has 2 or 3 modes of action going on here. First of all, you got a 5-15-5 fertilizer. This plot over here had just a micronutrient. Now there was a little N and K in that, but most of it was low levels of micronutrients. Here we're actually putting a 5-15-5 in furrow at planting time. So there's a nutrient base here at 5 gallons to the acre. Then Levitate also has a humic, actually it's a fulvic, a shorter chain acid in that mix, so they've added that energy. And then they've also got a biologic material. Now how they develop, that's their secret, but they got some kind of biological material, whether it's the biology material itself or actually the exudates that that's producing, I don't know, but that's in Levitate there. So they're trying a 3-way approach here. Put the fertilizer down that we standardly use, and then add this energy as well as the biologics to it. We also put radiate. Now that's a growth regulator. That's a growth regulator that's targeted to enhancing the number of roots that come out of this plant here. These are all stem roots, by the way. If these are not true roots, these are roots coming off the stem of the plant, the nodes on the stem of the plant. So they try to enhance that. So you can look at the ear size here, look at the roots here. You can see how they're trying to produce a lot of these little roots off of these brace roots that are coming out there. I think that's a function of that radiate. All right, this next product is called BioStrain. This is a Monty's product. I mentioned earlier it didn't have, I was wrong. It does have carbon in it. It does have liquid carbon, but it also has a biological product. And again, I don't know whether it's the actual bacteria or whether it's an exudate from the bacteria that's designed to function with the plant. But it's ideally, this product here is labeled as something you put on residue to help break it down. So in my opinion, they're using more of those mutualists or decomposing bacteria and less of those chemotrophs that we talked about earlier. So there again, it's awful hard to see a lot of difference in these ears, and you can see some of this root system here. All right, go to the next product here. Here's Levitate alone. I've already spoken about Levitate. Here it is without the radiate. So there you can see again the root system and the ear on that product there. So this is the only difference between this plot and the one right over there is the use of the radiate in that plot. All right, I've talked enough about that. Let's move to the next one. Here's a product called Sumagrow-Lux. You know, they ought to get an award just for coming up with that name. But I don't know much at all. If you read their claims, it talks about enhancing soil structure, about improving microbial root uptake. I mean, if they were all true, why, gee, I'd probably solve the crisis we got in Washington with this stuff. Maybe just sprinkle it down Pennsylvania Avenue or something. But at any rate, it's a biological product. I think most of it is actual bacteria and stasis that they're putting on here certainly has a very dark color. I wouldn't be surprised if it has a little humic acid in, to be frank. All right, this is a product called, oh, in fact, you can read that on the big sign. This is a product called Albit. Now, that's not a typo there, 0.2 ounces to the acre. Now, earlier I said this was live bacteria. I was corrected. That it's not, they put it, they hydrolyze the bacterial product. So in other words, it's gone into stasis. So it can be held over a period of time. So it's not as fragile as I first thought. But indeed, they're actually using a bacteriological product. And they've got some information on that. They've actually isolated what product that is and how it works in the plants, and got some pretty convincing science behind it. So at any rate, again, small amount applied. That's not a typo. We did actually go ahead and apply 0.4 ounces foliar to this as well. So it's got twice that, about 3 times that much there actually applied to the acre. Even so, a fairly cheap treatment there. So at any rate, you can see the roots. I did excavate this. Interesting, you can see how some of these roots are deeper and thicker than we've seen in some of these other excavated plots. All right, let's take a look at this next treatment here. Now, if you needed a standard to go by, this is it. Because this is nothing. Nothing. I got nothing here. Now, I didn't put a starter fertilizer here. All we've got down for base fertilization is what Richard Mann put on this field, which I think he did put some P and K down here. So that there's no starter on this plot here, so nothing. So you can take a look at the ear and root system here, and I did excavate this plot here. I did a little checking on this one with my little calipers over there. This is about 19 centimeters, the widest of this root right here above these brace roots, about 19 millimeters, which is not quite about 3/4 of an inch. And then I compared it to a number of treatments. Most of these are running anywhere from 21 to 24, so almost an inch wide on some of these roots. So there is a little difference there. So we'll see whether that relates anything to yield, but interesting on that note there. All right, come over here. Get myself out of the way here. This is Monty's liquid carbon alone. So no biological product. This is just energy. The idea is to drive energy. Yeah, like I said, you might think you're wasting your time here with putting humic matter on these dark soils. And that may be true for Richard here. I know he uses some manure, and it may be and that's a nice thing about manure, is it tends to give off a lot of short chain carbon. So we may be wasting our time here with this product, but a lot of these organic soils are a little short on some of these short chain carbon. So something to think about there. Here's the next treatment here. This is 10-20-7-0 at 10 gallons to the acre applied in a 2x2x2 band. In other words, a band on both sides of the row. You know, this is how we do it, isn't it? We just put the nutrient down and let the soil do its work. That's how we do it. Now, is that good enough? Maybe it is, maybe it isn't. I think that's why we're headed in the direction we are. We're trying to figure out, is there something more we could do? You know, you and I know, a lot of times we put down fertilizer and we get tissue samples back and say it's low in phosphorus or low in magnesium, and we're wondering, I put all that down. Why isn't it in that plant? And that's partially, I think, because of the way our soils are working. So indeed, we got to, I think about where these products fit and whether they can solve some of those problems that we have with just a straight fertilizer approach. All right, about to get to the end of these treatments. This is a product called Ag BioSelect or Ag Formula. Again, now this is a product marketed as a biologicals. There's no liquid carbon, no humic acid in this product. It's a biological product. The BioSelect was either added to the seed or put in furrow. We actually put 6 ounces to the acre in furrow. And then the Ag Formula was something you put over the top. We put 16 ounces to the acre about the same time we put that midnight on down there, about B3 or B4. So this is a straight biological product. I have not tested it before. The claims are that it can do, again, several things. So we'll see if indeed that's going to bear out here for us. Here's a product that's a little different from some that we've looked at so far, in that actually we added it to the starter fertilizer. So here we put the starter down, just like that plot right there that's indented on us. We put the same rate of starter, but now we got some biological products that are designed to work with the soil. We got both a seed treatment that has a bacteria with it that works then once it's in water and temperature. And then we've got a product called SP1, and that's supposed to work with the bacteria in the soil and the fungi to start building soil structure. And the thing that we've seen with this is a little more crumbly soil, a little softer texture on the soil as it works in trying to build structure in the soil. So we'll see how that works in this situation right here. So this is a biologic aimed at enhancing soil properties. And then finally, we've got this product here that's called Accomplish. Accomplish is in Levitate. It's the biological that's in Levitate. So here we have that biologic all by itself. See how well it performs or functions as its only component here without added fertilizer in this plot here. Several people have said they like these plots toward this end of the field. That may be true about the product's performance, or it may be true about the way the field changes here. So you got to be a little careful. We got replicated plots through here. So we'll get some good data this year, I think, in comparing these products head to head to head, and hopefully give you some idea. Like I said, we need to go deeper, though. If we're really going to understand these products, we need to know if indeed they're enhancing the carbon in our soil, or if they're indeed enhancing plant growth through the increase in beneficial bacteria. So that's really the standard I think we got to drive toward. These plots are useful, but they're not the final word, in my opinion. All right, we got a little more time. Any questions on this section? I got more to talk about. Don't worry. You're not going to get out early.
Are you taking leaf samples or anything on each one as you go through the season?
We did not here. And that, Darren, as I drove down from Columbia toward Fairfield, I thought to myself, you know, why didn't we take leaf samples on these plots this year? And you're exactly right. If we would have done ourselves a lot of good if we'd have gone in and done some leaf sampling here and looked at nutrient uptake, how they affected phosphorus and other things. We're going to add that next year in this type of test. But that's exactly right. You guys are on the right track in thinking about how can I measure this in a way that helps me understand how it's working. All right, come on over here. We'll get you out of the tent. I don't know what's shooting at me, but they did a pretty good job. All right, before I let you go here, I just want to say a few words about what I think was one of the issues that was on your mind this year. It certainly has been on my mind this year. And I'd hoped to get it in your mind way back in February and March at the winter meetings. If you remember, I talked about temperature. And if you don't notice, it was so hot this year. So temperature drives a lot of our issues in North Carolina here. And if you believe in climate change, I'm not saying I don't, I'm not saying I do. All I'm saying is if you think that's the direction it's headed, we're going to have to know more about temperature, because we're going to have to manage it better. We're going to have to manage it. If we're going to be successful with corn in North Carolina, we're going to have to manage temperature. And you might say, how in the world do you do that? Well, I'm going to show you a couple things we might think about in managing temperature. First of all, I want you to think about the 3 temperatures that are most important to corn. 86 degrees Fahrenheit, that's the first one. That's the temperature at which corn ceases its physiological development. Corn grows by a temperature clock, not by a time clock. It grows by temperature clock. So when it gets above 86, that clock stops. And it's a good thing, because if that clock kept on running as it got hotter and hotter at a faster and faster pace, this corn would be all done. We'd have harvested this corn a month ago. That's how much temperature we've had. So 86 degrees, the corn stops its biological clock and sits there, waiting for cooler weather so it can start the clock back again. So that's the first one. The second one, I think, what did I do with my chart? I hid it here someplace. There it is. Right there she is. The second temperature is 95 degrees. 95 degrees is the temperature at which the corn goes backwards. It doesn't grow forward. It doesn't stay still. It's going backwards. It's too hot. There's too much respiration activity going on to keep that plant cool. It's using all that energy, and it's taking away energy that's stored in the plant and all the photosynthate it can produce, and it's using it up. So it's going backwards. That's why we had short corn. We went backwards in late May and early June. All the energy that should have gone into making more cells was robbed to try to keep the plant cool. So it shortened up that plant, and we went backwards. So that's the temperature that we get worried about our corn crop at, is 95 degrees. Now there's a third one, 110. 110 is the temperature at which the leaf dies. The tissue, the cells die. They can't take that temperature. It's like cooking. Once you get to a certain temperature, the meat denatures and it's cooked. That's the way with leaf tissue. It denatures. You saw that. You're looking across corn and you see all these leaves in the top of the plant that have turned yellow. That's not nutrient deficiency. That's got too hot. Burned them. Now, most nutrient deficiency starts at the bottom and works up the plant. When you see browning coming from the top of the plant, that plant's too hot. It's denaturing. So indeed, those are the three temperatures we have to worry about with corn. Now, you might say to yourself, well, Doc, I don't remember that the guy ever telling me it was 110 outside. Well, there were a couple. I was told last time I did this talk, there were 2 days that were 110. So first of all, you're wrong. But second of all, that's, you know, in general, that's true. We don't get 110 degrees, thank goodness. But if you feel my pants right now, or look at my shirt, feel my shirt, you don't really want to do that. Too bad. My wife does it anyway. Anyway, it's hot. It's hotter than air temperature. That's because the sun is shining on it. It's transferring light energy into heat energy and warming up that fabric. That's what's happening on your leaf. As that sun directs hits that leaf, it transfers energy, and that energy, unless it's giving off water to take that heat away, it's warming up that leaf. So indeed, if we don't have enough water coming off those leaves to cool, that leaf temperature rises and rises and rises. So you can see here, we had temperatures, here's 110 right here. We had temperatures, at least at this canopy, at 32,000 in this field. We had these thermometers. Little bitty thermometers that were on the leaf here. Where did I put it now? There it is. Little bitty thermometers that we put attached to these leaves of these corn plants to measure temperature at that leaf there. And indeed, they were reaching up toward 110 degrees in this canopy up at Northeast Expo here, where we took these measurements there. There were 3 periods this year where these temperatures started getting in this range here. First period is before these were put in back in late May, June. That's back here. Here's this middle of July, or late June, 1st of July. There's July 1st right there. There we're getting toward the 7th or the 4th of July here. The third time is right back in here, about the middle of July. Again, we started peaking up in those high temperatures. So we've had 3 periods of that high temperature that we had to worry about. Now, the ones that when we talk about damage from temperature, the damage that I fear most is this damage, pollination damage. And we saw that. You guys, some of you have that in your field. It got so hot, it didn't pollinate. Cooked the pollen. Yet most of that is characterized by these tipping back of these ears. That's heat damage that caused that to happen in your field. Now, there are some fields that almost got no pollination. So indeed, it's severe. During that period of time, we could get up to 80% of our yield is lost. And you can see here, there were periods here in this 32,000 when we were reaching that 80% yield loss potential in that canopy there. All right, can we do anything about it? I explained the problem here Is there anything we can do about it? So we put these sensors on. We had 4 different populations at 3 different row spacings to see if indeed we can manage anything that pertains to our canopy to help our temperature. So the first thing is by row or population. The blue line here is 26,000. The red line here is 44,000. Here's July 4th. Remember, I just showed you that was one of our problem times, and you can see it spiking up here. This is noon temperature, and it's by seeding rate in a 30-inch row. So 26,000. There, this line here is 95 degrees right here. You can see at 26,000, we did not reach that critical temperature of 95. So we were, even though we'd stopped development, that corn was still moving forward. It was still making enough energy, more than it was using up. Whereas at 44,000, that temperature is 100 right there. It tipped right at 100. So indeed, population makes a big difference in what that canopy temperature is. This is why I mentioned last spring in the winter meetings. I said we're going to have to be more worried about population if these temperatures are going to be a problem, because the more plants we put there, the higher that temperature is going to be. You can see the difference if this, and a lot of corn was at the difference between pollinating and not pollinating some of that corn. So indeed, you can see the population had a difference there. The other factor we had, and this one surprised me, was row spacing. We got 20-inch rows, 30, that's the blue line, 30 inches yellow, and 36 is the green there. Again, just pay attention to the July 4th period there. These are noontime temperatures, and this is at 38,000. So this is a high population here. So again, you can see there's differences here. In fact, at 20-inch rows, we barely got over 90 degrees, whereas at 36-inch rows, we were at 105. And you can see some of these ears here. There's 36-inch row. At some of these, you can see this tipping. Now, these ears don't look half bad. You can pick some good ears out of even the highest population, but I can guarantee you that if you took 5 ears, you'd see a lot of this tipping and up and down at these higher populations. So it didn't, all plants are a little different, but you can see the overall effect there. I was surprised because I thought when we narrowed those rows down and we put all that canopy close together, the wind, that laminar flow of wind that takes away that vapor and allows more vapor to reach into the air would put a vapor pressure barrier there. That wasn't what happened. What happened was it was all about water. When we spread our plants out, we gave each one of them more water to work with. By putting them away from their neighbor, that's what happens when you go from 36 to 20s. You're spreading that plant out in the row. You're pulling it away. We had more water to work with, and that helped cool that temp. It's all about water through that plant. That's what temperature, how you moderate temperature. It's all about water through that plant. Somebody asked the other day, you know, what about more residue on the surface so we can protect that surface, what surface moisture we have? Yes, that would have helped. How about ripping in the row so we could get roots? Yes, anything you could do to get more water through that plant is important to moderate temperature. So this is our future in looking at managing temperature. You're trying to manage that water per plant. How is each plant receiving water? And if we can do that, we're going to have to think very carefully about how we increase population in the future. Be very careful about that. My time is up. Is there 1 or 2 questions that you had?